Good evening, dear ladies and gentlemen. I am Mangala Silla, Chairman, Civil Engineering Sectional Committee. On behalf of Institution of Engineers Sri Lanka, I would like to warmly welcome all of you for this lecture. Actually, let me give a formal introduction to today's our resource person. He's Professor Harsha Ranavira. He's the Vice President of the European Water Association and a Director of the Board of the International Water Association. He is a water and wastewater engineering professor at the Norwegian University of Life Sciences. He has ongoing relationships with Peradeniya, Jaffna, Rajarata, and Southeastern Universities. With that introduction, I would like to invite Professor Harsha Ranavira to do the lecture. So to you, sir. Thank you.
Thank you very much, and thank you for the invitation. So I came to Sri Lanka yesterday evening for my holidays, but I was invited to this lecture, so I'm glad to going to do this. So, well, after A-levels, I went to Ukraine to do my master's, and then to Norway to do my PhD. So the last 35 years I've been living in Norway. But all the time I have maintained the close relationship with Sri Lanka and Sri Lankan institutions. First 15 years with the Coast Conservation Department and the Marine Pollution Prevention Authority. So at that time I had projects with them when I was working at the Norwegian Institute of Water Research. And then after 20 years, I thought I should find a place to relax. Then I moved to university, but now it looks like I'm working even more than before. So I've been working at this university for now 11 years. Water purification, water supply and wastewater has been my main subject area. So the first, let's say first 20 years of my career, I was focusing on the processes, how to optimize the water supply and wastewater treatment processes. And while doing that, I saw the gap between process engineers and the control engineers or process control engineers. So 20, 30 years ago, we used remote control only to open a valve or a close valve. You know everything about that, Ganesh. But the world has changed now. So we can do a lot of things now, but it's so, we are developing so fast, and I can't even imagine what the world is going to be in our sector in, let's say, after 10, 15, 20 years time. Like I used to say is that our parents never knew about this, and even we didn't dream about what we can do when we were going to university. So now we are here, we can't even imagine having a life without this. So the whole world is going through a big digitalization process. So the water sector is not an exception. This way, not this way. So what I thought was that I can share some of the thoughts and some of the experience what we have related to the digitalization of the water sector. So I will say a few words about the digitalization word, and then opportunities for the water sector, and then challenges or threats with digitalization, because it's not only a positive side we are talking about, and some best practices where to find them. Yes, so starting with this one. So water sector is quite big, right? But I'm going to focus on a limited part of this water sector. So so if we look at some of the aspects, we have seen a remarkable increase of automation of our industry. which leads to efficiency in water purification and wastewater management processes, which also leads to the economy of our processes. So we talk about the water crisis, right? And then on the other hand, if you look around, we see seas, lakes, and rivers everywhere. We see water. In fact, 70% of the surface of the globe is covered with water. The challenge is that less than 1% is available for us, for mankind to be used. And we are not using that, we are not saving it, and we are actually misusing that. It means that we are not treating our wastewater, for example. 80% of the wastewater today in the world, they are discharged without any treatment at all, or inadequate treatment. So the climate change is making things worse. So we see now there's significant stress on water networks due to climate change, population growth, and increasing urbanization and aging and overly stressed infrastructure or the lack of infrastructure, right? So a country like Sri Lanka, I don't know actually the age of the drinking water network here, but probably 50 to 100 years, I would say. And most of the other countries like 50 to 150 years, and wastewater networks are also in the same age. How are we going to deal with that when we get either too little water or too much water? Population growth, we had 6 billion people in year 2000, and we're going to have 10 billion by 2050. But the amount of water we had in year 2000 was 200,000 cubic kilometers. It's going to be all more or less the same by 2050. So we already have problems with the lack of water. How are we going to deal with that? The population is increasing by 50%. The agriculture is using 70% of our water. And when 50% is increasing our population, the need for agriculture will increase by 70%. So we are heading for a crisis. How are we going to deal with that? We cannot build desalination plants everywhere. We need to find some other ways, right? So there we see a role to play by digitalization, making systems more efficient and also predictable. And I will come back to you with some examples of that, right? So the water utilities need to adapt to meet the emerging demands of a dynamic, highly deregulated and competitive environment. Emerging demands. If you think about the water quality, let's say 10 years ago, we had basic number of parameters we have to focus on. But the world is changing. Now we are talking about emerging contaminants, like what we get from the pharmaceuticals, all the personal care products, all of them, or like 70, 80% of what we apply, they go with our wastewater, pharmaceuticals. Our drinking water treatment plants, they cannot remove that to necessary levels. Our wastewater treatment plants, they cannot remove it either. So which means that they are in the circulation, the concentration is increasing, and we call them as emerging contaminants of emerging concern, because that we don't know what's going to happen when the concentration is going to be above the given level. So how are we going to do that? Of course, we have treatment plants. We know to a certain level how to improve the removal of emerging contaminants by adding new unit processes. But do we have space to do that? Or do we have money to do that? So here there are methods where we can use to optimize the existing treatment plants to make treatment processes more, let's say, more more optimized to do the job that we are expecting. That's why I'm saying that emerging demands, so the water quality requirements, legislative requirements are changing with the time. So if you take the wastewater, so some time ago, it was only removal of particles, then organic matter to reduce the oxygen depletion. And now we are talking about the eutrophication reduction by nitrogen and phosphorus removal. And in the European Union, we are talking about the removal of pharmaceuticals and all these emerging contaminants. So the challenge is the requirements to the water utilities stays as before. People expect to pay the same or less in the future to get better water, and also to have this freedom of opening a tap and get water from the tap and drink it without boiling and without thinking that you will get the diarrhea next day. So that's what Water Supply and Drainage Board has to do with. You cannot say that it's too expensive, you have to charge more. The technology requires more investments, so it will not be accepted by the people. So safe and secure drinking water and stormwater management and wastewater management. Stormwater is a big challenge in places where the climate change is impacting the precipitation levels. So if you take the northern hemisphere, especially in Scandinavia, so in some places we have the 200-year rain or 200-year floods are now occurring at every 50 years. So how are we going to do that? So what are we going to do that? Can we build stormwater networks? No, it's not possible to build physical stormwater networks to take rainwater out of the streets. We have to find a new ways to manage these conditions. So digital solutions, automation, surveillance and automations are some of the examples where you can use these concepts. Okay, so if we look at the big picture of water, we talk about the water use in irrigation and agriculture, flood management, hydropower, water saving, industries, aquaculture, and probably this list is not complete. Then we have the water supply and wastewater management. So in this presentation, I'm going to focus on this part because this is the part that which I know best. But we can discuss about some of these issues if there's any interest. I can comment on some of the issues, what they are doing now, and what is the experience, and which way the world is developing. So if you take the water supply and wastewater management cycle, we take water from a river or a lake or groundwater, and then we transport them this way, right? This way. It's yeah, right. Okay, thanks. So we take water from a lake or a river or groundwater, and then we transport that to a drinking water treatment plant where we do the purification process. After that, we transport that water to the households or the industry. After that, we collect them. Maybe towards the end of this lecture, I will learn how to use this. So we collect the wastewater from used water from our houses and industries, transfer them through pipe, a network of sewers to a wastewater treatment plant, and then treat the wastewater. After that, we return that water into our water resources, recipients. This is the normal cycle. And if you look at these small boxes, if you can read, This shows that each and every step, there are possibilities to have digital tools, IoTs, to monitor the status and also to control the quality or the status and to make the process more efficient and more economical. So 10, 20 years ago, we didn't have this picture. This is becoming more and more a norm. So this is why I'm saying to my students that you have chosen the best, one of the best jobs or the professions in the world, because you will always have a job, because this is not going to end. Okay, so what are we talking about? We are talking about making our processes, utilities smart by design. So they have to be adaptive. They have to be adaptive, distributed, and advanced. Adaptive means that we cannot build a treatment plant today to cater only for today's needs. We have to think about what's going to be in 10 years' time, in 20 years' time, and most of our treatment plants in Norway, we are, at least the big ones, or let's say if they're the size of 50,000 people or more, we develop plans for the next 20 to 50 years' time. Population increase is very low in Scandinavian countries, so we are talking about like, say, 1 to 2% within a 10, 15 years' time. But there are other situations are coming up. The legislative systems and pollution is increasing, and the other demands. So how we have to build our treatment plants to be able to cater these systems, right? Smart use, doing more with less. Of course, we all do more with less now, or at least we do more with the same time we had. Our parents work 8 hours per day. We worked 8 hours per day 20 years ago, but imagine how much work that we produce within 8 hours per day now. Still, we are behind the schedule all the time. So it's the same way like smart use, doing more with less. Some example is that the land area is a challenge for also for the water sector, because if you take the mega cities, there's no space to build a new treatment plant or expand a treatment plant in order to cater the increasing population. Even if you find a place, the water authorities or municipalities they cannot afford for that land, because real estate developers will bid much more. So how are you going to do that? So you have to find a way to add on or increase the treatment efficiency and capacity and efficiency in your treatment plants without expanding your treatment. Here, there is a possibility for you to use digital tools, right? Smart control, I will focus more on this, how to use sensors and how to use sensors with less investment. Okay, so here, if you look at the last, let's say last 10 years, the SCADA systems, which are the control systems of any treatment plant or a water treatment plant or a wastewater treatment plant. So they were not so common, or they were more expensive 10, 20 years ago. But today, even a very small treatment plant, they will have a control system. So they're accessible, they can do more, they are cheaper, they are affordable. And then there are a lot of online sensors. Real-time water quality measurement has become a norm in our industry. They are affordable, there are plenty of them. And we can also measure these water qualities. There are sensors, physical sensors to measure water quality. Most of the parameters can be measured, but the cost is a different story. So then we also have huge operational databases, because these online sensors, they collect, they can produce, they can generate water quality data every second or every minute. So we get huge amount of data operational database, and we can use this data to generate we can use the modern tools like machine learning and AI, and then we can generate systems to improve our treatment processes and also increase process knowledge. We know much more about the, let's say, coagulation process or the disinfection process or the biological treatment process than 10, 20, 50 years ago. So this gives us an enormous opportunity right, enormous opportunity to improve our digitalization process. So here is an example of what we are talking about in financial terms. The SCADA is the process, the control systems, the supervisory control and data decision system, which is not only water people are using, it's all the process engineers are using, right? So the market for water and wastewater management predicted to reach 2.2 billion by 2025 and increase from 1.3 in 2015, a doubling of investment only on the process control system. So what are they going to use that for? To monitor what's happening and also to see what can we do better than before. So we talk about the digital water, smart water, Internet of Water, Water 4.0. We talk about the same thing. So from next year, our university, we are starting a new 2-year master program called Intelligent Water. So it is about how to use digital tools in water management. So of course, if you Google smart water, you will find a lot of universities are offering that. We thought we cannot offer the same, so probably the content is more or less overlapping, but we found a new word, intelligent water systems. So we are talking about efficient collection and use of digital data for smart digital solutions to address the challenges in critical physical assets and the services. So water supply is treated as a critical service in most countries in the world, and I guess it is also in Sri Lanka. So this is also an aspect I would like to come back to, because imagine the disinfection process. It's not functioning in the water supply system, or someone deliberately change or manipulate the disinfection system that the operators thinks that it gets the correct dosage, but in reality, it gets only half of that. That will cause a diarrhea for hundreds of thousands of people in a urban area like Colombo. So it can paralyze the whole society. So that's why the water supply is treated as a critical services, because if you don't have water, then you can disrupt the normal function of a society. So here we talk about sources and environment, so watershed, surface groundwater, water reuse and wastewater effluent, and then the collection, treatment and distribution network, and finally the end customers, the residential, industrial, commercial and industrial, and water for the nature. So in each and every place, we have the possibility to use digital tools and the big data and data technology to make our systems more efficient. So opportunities for the water sector. Yeah. So I have 2 slides with these small fonts explaining or elaborating some of the benefits for different segments. So community benefits, improved long-term affordability of rate structure, greater transparency in the use of proceeds from water tariffs, reduced likelihood of bill shock, non-payment and cutoff. So here I not sure how relevant this is to Sri Lanka, but it is about when you know the what do you pay and what your money is used to, and you will know that how your let's say, how can I get an example? So the mobile phone bill, it's seldom that you will exceed or uh, you will get cut off your mobile phone bill, because you can at any time you can check how much is left or when do you have to pay, right? So in the water system, it's like that. So you will know that what is happening and how much you have to pay, what is the quality. And if you take the customer experience, increase customer engagement and responsiveness. So in some countries, especially in the European Union, there is a requirement that customer, we as the end users, we have the right to know the quality of water which we get in the tap. So how can this, how how are the plants, treatment plants are managing this? Because they cannot monitor water quality every day and publish it. So for the time being, it is allowed to publish water quality once per month. This is going to be changed. People will ask that, I need to know that what's the quality of my tap, right? And what they publish today is the water quality which leaves the treatment plant, but not what you get in the tap. So there's a big difference. Because all days that both drinking water pipe and wastewater pipes, they're put in the same ditch, and after 50 years or 100 years, both pipes starts to leak. And when there's a vacuum, so it sucks in from the one pipe to the other, and then you have highly polluted water, although the water left, when the water leaves the drinking water treatment plant, they were in the perfect quality. But people will not accept that in the future. They will require, they will demand to know the water quality in the tap. How are you going to do that? And they will not, probably they are willing to pay a little bit more, but not the double the amount, right? So here says that customer experience, reduce disruptions in water services, because that with digital tools, we can predict the remaining lifetime of our network. We will also know that in which places there's likely to be a leakage because of the corrosion. So all this information will increase the stability of water supply in an urban system. So a reduction of the volume of disruptive construction projects, because you can plan it better. Environmental protection, reduce risk of sewage overflows into the environment. So in most cities, both wastewater and rainwater, they flow in the same pipe, combined sewers. When you build a new sewer network, so we try to build two lines, one for the rainwater and for the wastewater, but it is easier said than done, because it's such a huge cost to do that. But what happens is that if you have everything in the one pipe, when there's a big rain, then the capacity of that pipe is not enough to transport both rainwater and wastewater. So either it will overflow, then the city will be flooded, not only with water, but also with wastewater. And it will also pollute your water sources with that. But there are ways to manage that without expanding, physically expanding the sewer. So one example is that if you take a city like Colombo, when there is a rain in the southern part of the city, you will probably not have the same amount of rain in the northern part of the city, right? So imagine that all sewers are connected to the trunk sewer, and sewers usually have some reserve capacity. So the sewers are not filled all the time, right? So what we do in one of our pilot projects, what we suggested was that when there's a rain, that we will give priority for that area sewers to transport water and wastewater to the pipe, while the places, the area where there's less rain, we will stop pumping from those sewers into the trunk. So they can tolerate to have sewer accumulated in the sewer will be their pipes for, let's say, 4 hours or 8 hours or 16 hours instead of pumping that to the main trunk, right? So then you are utilizing a hidden reserve in the water network. So thereby you can reduce the pollution levels. Operational benefits, data-driven operations and decision-making reduce errors because the operators, in most cases, operators are based on their experience. And they know that if there is the incoming water has higher turbidity, they have to increase the dosage of alum, for example. But what do you do if that experienced operator is not there anymore or he is sick? So this is what the digital tools can take over, right? So because that we have a large operation, the historical database, and also we can develop algorithms to, let's say, simply to predict the optimal alum dosage, depending on few parameters of the water quality, you are no longer dependent on that experienced operator. So an experienced operator may be good enough to deal with removal of, let's say, turbidity after a rain, erosion based. But if you're talking about the removal of pharmaceuticals, emerging contaminants, and several other parameters, it's impossible for a person, even with the knowledge that you and I have, it is impossible to do it manually. So this is where the digital tools can handle. So then these digital surveillance systems and process control could be included in the decision-making systems. Predictive maintenance, that means that you will know that how long you have again before you have to replace this pipe. I have seen some couple of projects where there are systems to measure the thickness of the sewer without, no invasive methods. So usually what we do is that we send a robot with a camera to take photos, and then you can see how the surface is, and then you say that, okay, here it's likely to happen an accident in the near future, so we have to start repairing. But instead of that, on top of that, you can also get other measurements like predicting the thickness, and then you can say that here, now we have 100 million rupees to repair or rehabilitate our sewers, and this is the places that we should start rehabilitating. Reduce downtime and critical assets, regulatory compliance, because we will reduce the number of incidents with non-complying treatment efficiencies. Financial benefits, reduced operational expenditure, because we can reduce the chemical usage, reduce the energy usage, reduce the transport, reduce even the volumes that we are dealing with. So at the end, we can see it as a profit or less costs in our accounts. Reduction of costs and risk associated with ad hoc field maintenance, increased capital efficiency because of targeted rehabilitation and faulty infrastructure, increased revenue because that probably you are experiencing also in Sri Lanka, because I guess that you have water meters. And then when we have water meters, from one side, people will use less water because they are concerned about the amount of water that they are using, what they have to pay. And on the other hand, that when you have a meter, then you will be paying for what you use. Increased resilience, operational flexibility, workforce development, and brand and innovation. So the water sector, of course, drinking water sector is quite fine and people know that is good. And the wastewater. So we have a problem to recruit young undergraduates to the work with wastewater, especially the girls. They don't like to work with wastewater. We have to change the brand, and we are not talking about water and wastewater anymore. We say that it is for the water sector. For some, it's important. I couldn't understand it before, but I understand it now. Because we have to think a lot of things when you're talking about. And then for the compliance, we just need to measure the water quality of the water which leaves our treatment plant, drinking water and wastewater treatment plant, right? It's not like that anymore. In wastewater compliance systems in some countries, we have to report the treatment efficiency, removal efficiency, not only the effluent quality. Drinking water, of course, effluent quality, right? So if you want to report the treatment efficiency, you have to measure the water quality at the end and also at the beginning. That's also fine. You can have few sensors to do that. By the way. But how do you optimize? Because now our treatment plants are not simple, not as simple as before, like you just have a filter and disinfection, but we have, say, cross filter, pH adjustment, coagulation, 2-media filter, activated carbon or powdered carbon, and disinfection. So how do you optimize these processes? If you only know, or if you only measure the inlet and outlet, you can't do that. So that's why in most of the medium and large scale treatment plants, we measure water quality in between these processes. So then we know that where the highest potential to improve the water quality or optimize the process, and where there is the problem. So especially if you have if you take the wastewater, so here is a picture of physical, biological, and chemical processes. And you need to find the balance. You need to know that how much should you remove by coagulation and how much you should remove by biological processes. And to do that, you need to measure the water quality in between. So now I would like to show you an example because I would think that now you understand that, yes, we need to measure the water quality everywhere. So how are we going to do that? They are so expensive. So, for example, turbidity measurement is that you take a water sample and put your small small instrument, measure the light refraction, and then you get the turbidity instant. But if you take for the wastewater, then the compliance requirement is not about turbidity, but about suspended solids. The suspended solids measurement, it takes quite a lot of time. Like you take sample and then you filter through, let's say, 1 micrometer porous filter, and then you dry it, and then you weigh it, and the weight difference divided by the volume, that is the suspended solids, milligram per liter. This process takes like 2 to 3 hours. This is a couple of seconds. So the soft sensors means there is a very good relationship between turbidity and suspended solids. So there are a lot of suspended solid sensors. They are not measuring suspended solids, they measure turbidity, but they have the algorithm to estimate the suspended solids using the turbidity measurement. So this is the basics of a software sensor or a virtual sensor. So the same concept we can use in to measure many other parameters. So like here in the left side, you see number of parameters which can be measured using physical sensors: flow, suspended solids or turbidity, pH level, chemical dosage, redox, conductivity, UV, and all these are, I would say, they are more or less affordable, and they are not so messy in daily maintenance. But if you take the parameters the other side, they are much more expensive. Like a COD measurement is, we are talking about like $20,000 to $30,000 per one sensor. Phosphates, 50,000, 60,000 US dollars per one sensor. Nitrates, 10 to 30, $40,000. So even very large treatment plants, they cannot afford to have these type of sensors. And when you have several plants, a big plant, then you have several lines, and you actually would like to measure the water quality in all the lines. So here we have developed a sense system called hybrid sensors. Hybrid sensors means that we measure some of the, not all these parameters, maybe 2, 3 parameters, which are affordable, which are cheap. For example, flow, pH, turbidity. And then we have an operational database, historical database. And then using that, we generate an algorithm. It can predict what is the COD, BOD, COD total oxygen demand, phosphorus, and nitrogen species. The cost of this sensor is going to be like 10 or 15% of the physical sensor. So here there are some examples of publications which show that how good we have managed to develop a sensor for phosphorus, total phosphorus, and COD. So right now, these sensors are in operation in 6 plants in Norway and a couple of plants in China. So it's possible. Now, the next step is to develop such a sensor for emerging contaminants, because the European Union's revised drinking water directive, which was revised last year, requires all drinking water treatment plants to measure emerging contaminants in all drinking water treatment plants. And one test costs 300 euros. And it is not only once a year you have to measure, right? So how are you going to do that? So that's why we are working on developing such a sensor for emerging contaminants. What we see is that if we combine the UV, visible, and also fluorescence spectra, then we have probably a possibility to develop this type of a sensor. And measuring UV and visible spectra plus fluorescence is not that expensive. So the other, where the world is moving is that digital twins. You have heard about digital twins. So digital twins means that we have data collecting from all the sensors, and then we have models where we can use these models to predict different things. And then we have the operational data and machine learning system to update these systems. And finally, we have a system to visualize this, how it looks like, right? We can walk through a treatment plant digitally. We can say that, yes, I would like to see the water quality here, incoming water right now. I would like to see the coagulant dosage. And I can walk through the filter system and see that how it is functioning. Okay. So the whole picture is there. Not only the operator, but all the manager and researchers and everyone can see all these data online. So this is an example of visual tool, how we use it in wastewater treatment plants. Here you can see this, the inlet, outlet, and the dosage here, suspended solids and dosage. And then we have these traditional trend curves. And all this information are combined with models, simulation models, and then put into a 3D model. So I was attending the IWR's Digital Water Summit a month ago. I think over 90% of the presentations were talking about digital twins. So it's going to come to the water sector. Something else is that how we can predict what's going to happen in the future. So right now, we know that water is coming, especially in if you take water from a lake, then it's fine. You don't have to worry much because the water quality is more or less stable, at least during the seasons, right? But if you take water from a river, the water quality, raw water quality changes so fast. You cannot even do 2 jar tests per day to define the dosage. You need to have a different, the other approach, right? So here what we have tried is that to predict the output quality using operational data, historical data, and the process knowledge to predict what's going to happen in 2 hours, 3 hours, 5 hours time. So you can see that this picture is about 6 months old, but we have come a little bit further. And when this is for 30 minutes prediction, 1 hour, 2 hour, 4 hour, 8 hours. So when it's prediction time is longer, then the accuracy is also getting weaker. But these are first approaches in this concept. So we are going to see these type of systems. So we don't need to wait until we take the water sample at the end and to say that it is good or bad. Already now, when we are adding chemicals, we can say that what is going to be. Right? And then you can, if you know that it's not going to work well, then you will know that what we can do, what we should do to improve our system. So then I would like to focus on the downsides of digitalization. You have probably seen these type of newspaper articles. In fact, the water sector is the third largest sector of all the industrial sectors where the cyber hacking is taking place. It is not new. It started even 20 years ago. And here is a story or the historical events in US, UK, and a couple of other places. You can see that every year something is happening. And these frequencies more and more, they are increasing. So cyber attacks are not new to the water industry. So risks from digitalization, risk of technical failures. We are putting our online sensors into our water quality system and we think that it will work, but there is no sensor which works 24 hours per day, 7 days a week. We cannot let everything to be managed by sensors. It's easy escalation from a single unit failure to system collapse because we are connected. We are making our system much more dependent on automation. Do they make our operators less knowledgeable? Professors, I get this question many times when I'm talking about digitalization and automation, because they say that, yeah, if you have this type of system, our operators, they will never learn, they will never think. They think everything will be done automatically, like the new cars, In our parents' time, even anyone who owns a car could do some repairs in their cars, right? But some of us, we don't even know how to open the bonnet because we have let everything to be taken over by this automation fancy things, right? So causes increased risk of cascading, increased vulnerability of process stability, yes. So there are many reasons why this could happen, but malicious actions like cyber attacks, this is what we are going to focus on, what we should do, what you should think about, right? What can cyber attacks do? Interfere with operations over and under dosage. So it can double or it can increase 50% by alum dosage. It will end up in, the result will be that increased aluminum in our treated water. Increased aluminum in treated water can cause Alzheimer's disease. Unauthorized changes to the program instructions. Let's say operator will not know, but someone can go into our systems and say that, yes, increase, decrease, or stop dosing, modify control systems, produce unpredictable results, drive the whole process crazy, block data or send false information to operators, change alarm threshold. So when you have these automated monitoring systems, we can say that, okay, if pH in this plant, pH has always been between 5.5 and 7. So if it shows 50, then something is wrong with either with the water or the sensor, but most likely with the sensor. So then there's an alarm. But a cyber attack can make that alarm level reduced to another level, so the operator will not know. The operator will think that yes, everything is fine, right? In reality, it is not. Ransomware, they can block the system and ask for money. The biggest challenge is the unawareness. If you ask our treatment plant managers, they would say, no, our plant is safe. Unawareness, it goes with unpreparedness. So when you are under attack, then it's impossible to think properly. That's why we advocate. Think about this, make your system prepared. And here you can see some newspaper articles saying that why it has happened, why the all of impacts have escalated to an unbelievable level. So there are good strategic principles for secure water against cyber threats. Understand the threats. You need to know that what can go wrong. Manage risk, develop and implement approaches to manage risks and address cybersecurity vulnerabilities. So what is the world's most common password today? It's still 1, 2, 3, 4, 5, 6, 7, 8. You cannot use these type of the weak and safety systems if you are working with big water treatment plant. And during the COVID, this has escalated because when the COVID came, well, the operators, they could not go to work. Then many treatment plants say that, okay, they can work from their home, and they open the process control system to be controlled by home operators. And many places, many homes, or many operators, they didn't have computers. They had to borrow their kids' computer, or the kids were playing on the same computer. The security was so in such status that it is. We are talking about European countries and the US. What happened? Where it happened? So we were not prepared, and this has increased the vulnerability of our water and wastewater system. Develop capability, manage incidents, respond effectively with industry to any serious cyber incidents, including those that compromise critical water infrastructure. Manage incidents. You have to plan. You need to have a system to manage them. Develop capabilities. You need to know that specialists who can deal with if something goes wrong. So if you have a fully or advanced automated system, and it was supplied by a consultant or a consulting company, which takes 2 days to respond, you cannot live with that. In the future, you need to have in-house capacity, or you need to have secure access to those specialists to respond promptly. Strengthen collaboration. So another biggest challenge is that when cyber attack happens, the plant owners, they don't share this information all the time because they are ashamed of having such an attack in their treatment plant, and they're not sharing this information. So it's encouraged to share this type of information, so so that everyone knows that what can happen next, right? So managing cyber threats, awareness, prevention, detection, response, and recovery. So these are important parts in the system. So the key to reduce risk is to know your risk. Preventive measures work, and so does the preparedness when dealing with the post-attacks. So best practices, couple of slides where you can get more information about these systems. IWA stands for International Water Association, and there is a program called Digital Water Program. A lot of free resources, reports, expert advice you can get, and also there are strategic documents developed by a number of countries, which are also freely available, which describes how to deal with this. And then there are nice documentation about where the digitalization is going in the water sector. What can you do and what do you see in the future? So yes, so these are good practices related to cybersecurity, and this is what I wanted to share with you in the water utility and water supply system. So there are some more information I can share it with you, but I would be happy to answer your questions.
So these sensors go into the water body, or is it really, when I heard online, I thought it's really from the internet, not online, no, online.
Well, maybe the correct word is real time. Real time means that you get the measure, you measure the quality in real time. So then there are different definitions like online and inline. So inline means that when you have the sensor inside the water body,
Yep.
Online could be that you take a small bypass, because if the pipe is so big, like 2 meters diameter, then you don't have a possibility to measure it. So you take a small side line and you measure the parameter there. So sensor itself is, or the concept is the same, right? But this construction could be different.
Okay.
Thank you, Professor Harsh, for your interesting presentation. With regard to the cyber security, I think water board, we probably now going towards online billing and so on. So there we find it, there will be a threat for us other than the other like operational things, because we are still managing with the jar test all the plants we have where we have this uh, conventional water treatment, coagulation, flocculation, sedimentation, and filtration, chlorination, and so on. But we have few source and filters there. You don't need to do that. And the other thing with regard to the I mean, you said about the emerging contaminants. So there we are not moving rather than analyzing them. Instead, we are trying to manage it differently than other countries probably. So we developed a policy in 2009 and we got the board of directors approval. And now it has been even published at the David Publishing New York, when I presented the case. So what we are trying to do is now we are getting grant money from the ADB, Knowledge Support Technical Corporation. It has been already awarded today. I received it is officially awarded. And where we are trying to now, we have main critical issue is emerging contaminants from hospitals, laboratories, beauty care centers, and so on. So there we are trying to, we know now, for example, xylene, ethidium bromide, DNA marking that is carcinogenic. Then we have the amalgam where you use fill up tooth cavities. Then we have xylene, for instance, hospitals where the PVC pipe becomes soft. So all these stuff at the moment, they are, uh, and the formalin, which used to preserve the body tissues after operations. So like this, now what our strategy is, and also in case of cancer patients, especially the goiters, they use iodine 131. So we know we can go delay and decay for that one, radiation levels. And in Atomic Energy Regulatory Council, they check it and then only we discharge it. Like that, we know some parameters, but we don't know all the chemical groups, what the kind of pre-treatment that we are going to do. And we are trying to develop a pre-treatment strategy for each chemical groups and to bring them to the domestic nature. So that is our aim, because in our context, it's very difficult for us to, monitor them. So instead, we have to manage it differently. Even the microplastic issue, we are hoping to, most literature it says that we are removing, if you have a very good biological treatment, we can remove more than 80%, 90% with secondary treatment in the biological treatment. So that's how we are approaching completely different to the Europe. And for the wastewater treatment plants, we have the SCADA system to operate. Like 2012, we have two treatment plants. From there onwards, it's already we have the SCADA system, and we have main few parameters like temperature, pH, DO, online monitoring, and DO. Then we have the MLSS online, and the flow at the final level. And we have our first preference goes to nature-based treatment. Wherever we find adequate land, where we have the reuse potential, we go for waste stabilization pond systems. And our aim is to recover the algae as a biomass, as a renewable energy in future. We are already doing carbon footprint studies. So then we have the aerated lagoon with maturation ponds as the second when we have moderate land availability. But when we have the lands are scarcely available in the densely populated area like Soisapuro, is surrounded by the housing scheme, we go for fine bubble aeration. We don't go for mechanical aeration because that will provide aerosols that will travel with the wind. So they have to be go for fine bubble aeration with 4-meter deep water tanks. With the blowers, all of them have the VFD, variable speed drives, and also like that, that is our strategy. And if we are discharging to sensitive water bodies like lakes, we go for biological nutrient removal. We go for reverse APO process, where we have the anoxic, anaerobic, and aerobic. With that, we are removing VOD less than 8 in most of the treatment plants. And our strategy for when we are discharging upstream of the drinking water intakes, we go for UV disinfection against chlorination, because chlorination can produce the trihalomethanes, and then we will be extracting there. So to have it, we don't have residual effect from UV. So when there is drinking water intakes, like for example, Candy City, we have ultraviolet radiation.
Very good to hear, and also I can see that you are very knowledgeable about what's happening in the system. But all these concepts have both positive and negative sides, right? So Candy City, UV, perfect. But how do you deal with if there is a leakage from sewers getting into a pipelines, right? One of the biggest advantage with chlorination is that you have the residual effect. It will kill whatever it needs while it is transported from the treatment plant to the consumer, right? And then here also we can have some digital tools. They are used in a number of cities. So you can have boosters. I don't know whether it's used here. It means that if you add chlorine at the departure from your treatment plant, and the last consumer is, let's say, 20 kilometers away or 50 kilometers away, and by the time that water reaches to that level, okay. Chlorination, yeah. Okay, fine. Yeah. Yeah. Okay. Wastewater. Okay. Right. Then I can understand. Yes. But if you take the residual chlorine, the issue is that you cannot have enough chlorine leaving and when the water is leaving, so that all supply chain will get enough chlorinated water, right? So that's why you need to have, or you can have systems to measure the residual chlorine, and then you can have boosters. Right. Right. Yeah. Okay. Yes. Yes. But you have only one secondary chlorination place, right? Yeah. 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 So this is where you can use digital tools, right? You can go for online or the real-time measurement of residual chlorine, and then you can also have a dosing connected to that. Right? But when it comes to the emerging contaminants, of course, reduction of from at the source is the best way. And then if the hospital waste are the notorious part, right? You have to deal with that. But again, how do you deal with the pharmaceuticals? Sri Lanka is a country, anyone can go to any pharmacy and take from, and even if you have a viral fever that you are taking so much medicine, right? So what is the percentage? Only a fraction of those pharmaceuticals will be absorbed or destroyed, degraded in your body. The rest is going with your wastewater or when you flush it, right? And all the creams that our ladies are using to be, for young forever, they do the job, but these products, they don't get destroyed in the nature. And we can't remove it in our wastewater systems, and they're accumulating. And then in the many Asian and African countries, the wastewater is not treated in wastewater treatment plants, right? It's their septic tanks or the other local systems. And the fate of these emerging contaminants in these systems are not well known. So, but what you're doing is great, because in many places in Asia and Africa, they are not thinking about this. Okay, you mean which are not used? Yes, right. Very good. But don't think that it will solve your problem. China, yes, very good. They are supporting. 70% of their rivers have much higher concentration of pharmaceuticals, right? They can't solve that problem. In some places, there are some stretches of rivers, the concentration is so high. I mean, we haven't seen those types. We are talking about milligrams per liter, right? So those are huge, huge amounts, right? So having one facility, that's a very good start. And then you will also got the knowledge how to deal with that. But we also have to live with this understanding that we cannot control everything. People will continue to take medicine. People will continue to take creams, bitter creams, right? Well, 70–80% of that, it goes with the shower.
I believe that, about the heavy metals. Now, I don't know the situation here. I was told that heavy metal are not kind of, removed from the system. There's no facility in Sri Lanka. But what about in the European countries that you come from, the developed countries? Because now increased use of batteries and, circuit ICs, integrated circuits, they contain some of these heavy metals, including mercury. Now, I know Sri Lanka, the disposal is not properly working, although there are some regulations and methods are using it. So ultimately, it will end up in reservoirs and maybe coming back into the drinking water system. Because in Sri Lanka, countries like Sri Lanka, it ends up in rivers, and then there is a possibility because heavy metals you don't need to take a large amount. I mean, small amounts, and the body cannot expel it. The other thing is, actually, you very rightly pointed out the security, the cyber security. See, everything is okay as long as you have a very kind of limited operation, kind of a small thing, in-house. The moment you open it out to the internet, the risk comes. See, as long as now, this gentleman, Zamit, I think he's very knowledgeable. He said a lot of things. But then the moment you open it out to the internet, then the bugs will come. So you never know where the bugs will come. And if anybody is, I mean, if a hacker wants to do it, he can definitely hack it. There is no question about it. Because what you need is, there are now various things, they call it worms, they don't work immediately. They are hiding, for an opportunity, for an order. Now you find that increasingly these things happening. So what can we do about it? I mean, maybe you can say something. Maybe this gentleman also, who is very knowledgeable, can enlighten us. Thank you.
I can start and Ganesh can continue after that, right? Okay, about the heavy metal situation, right? If I take the situation in Norway in 70s, 60s, 70s, and 80s, that our wastewater had quite a lot of heavy metal concentrations. Because of the improper disposal of solid waste, including batteries and paint, remaining paints and everything, right? So it has changed radically during the 90s and 2000, and to the level that we are one of the few countries in Europe where our wastewater sludge could be applied in agriculture without further treatment. So if you take Poland, Hungary, and even UK, it is not allowed because the heavy metal concentrations are still too high in the sludge. Because if you have heavy metal in wastewater, it has to end in one of the two phases, right? Either in sludge or in water. So we try to remove them. So because most of the heavy metal will be associated with particles, the ones they can be associated, but of course there is the dissolved part which goes with the water, right? So removal of heavy metals in drinking water is quite demanding, but this is done in, for example, in Japan, in most of the drinking water treatment plants, they have continuous measurement of heavy metal concentration. because they know that their water has industrial discharges coming out, right? There are methods to remove, of course, but at a cost. And when it comes to cybersecurity issue is that yeah, we know our mobiles are under attack, right? All our mobiles are connected to internet, right? How the Google map works. How does it say that, oh, there is a traffic jam there. It's going to take 4 hours. It's continuously sending in information for each of our mobile to somewhere, and we process and you get it back, right? So if a hacker wants, as you correctly pointed out, it's an easy, very easy job to disrupt the whole system. But the downside is our treatment plant managers, they don't think that our system will get attacked. I'm not saying it is only in Sri Lanka, everywhere. Everyone thinks that this is safe enough. And if you look at the history, and you can see that these are not small plants, or these are not nations where they don't have enough money to invest in, but still they get attacked. So this is one of the threats that we have to live with, because the digitalization is a process that we cannot stop. We will install more and more online systems. We will get third-party suppliers to access to our water treatment systems, because we are moving even from physical. We are now in many process control systems that they are not using PLCs, and they are working with the cloud systems, right? So you send information up there and get it back. You're opening your system to a very unknown number of parameters. Yes. Yep.
The question regarding the heavy metals in Sri Lanka, for example, we have the industrial siting policy, which was joint cabinet paper prepared by Water Supply Ministry with the Ministry of Environment. So there there are type A industries, type B industries. Type A industries are the high polluting industries, like for example, tannery, steel, like that, which is washing and dyeing plants, so on. So with this policy, which was approved in 2010, they prohibit. You can have a type A industry, then you have to go vigorous EIA process. That is the only option to have a location of a industry in upstream of the drinking water intake. So that will safeguard the upcoming industries. So that's why you can see we will manage to relocate the plant in Borana to Eraul because of it has contradicted the industry siting policy. So we have a very strong siting policy. And the other thing about the heavy metals in the wastewater treatment plants, we are following the EU Council directive. We have prepared the interim standards in CA, but unfortunately it was not, still could not finalize it. But the standards are very much in line with the EU Council directive for, using in the farmlands and land disposal. So our heavy metals are very much within the limit of that. We are analyzing it. It is under the EPL, Environmental Protection License, we have to get every year. So we are monitoring that one, and also we have also checked the them independently, because if we try to do it water boards, no one will accept it. So we have Dr. Sudarshan Fernando did an independent testing of our sewage sludge in our Soysapura plant, where we have 200 more than 200 industries connected, and they did it in the Nanotechnology Center, Sri Lanka Nanotechnology Center, and they have recommended our sludge is very much safer. They check with the EU standards, many other standards, Sri Lanka compost standard, and check direct application of the sludge. and we are quite safe. But to make it better, they have recommended 1/3 of sewage sludge against other material for co-composting, because our sludge contains very high phosphorus, because we have the biological nutrient removal plant. Phosphorus accumulating organisms are very much in the excess activated sludge. So likewise, but then for the better compost, we need to have other material to make the better properties of the compost.
I have no doubt that you have very good policies. It doesn't solve a thing. Believe me. EU countries, you are referring to the EU policies. Of course, we have very good policies. More than half of our EU countries, they are not even close to achieve these issues. Of course, you will be the plant, it will function. And whenever you measure it, it will work. It will see all the documents are fine, right? What about the times when they are not measuring? Do you have a continuous measurement system? Do you have a sampling system, right? And apart from that, there are other places in the country where there are industries, right? So, and think about the batteries, household batteries. Yes, so industries you can control, but batteries are becoming like almost like a non-point pollution source, right? So one idea that I was promoting in some of our projects, start with the kids at the school. Let them know that yes, you are not supposed to throw your battery into the garbage or to the sewer, right? To collect it. So it's almost impossible to teach adults, right? But the kids, they will, if you explain it in a good way, that they will do it. So I think we need to also think about that. Start with these type of activities.
Yeah. Study is that the TDS value, total dissolved solids in drinking water, they are referring the drinking water, the storage. Therefore, in Sri Lanka, they request to boil and drink. They are in the media also. Is it correct? What is the TDS level of drinking water in Sri Lanka you are giving in the tap or the urban water? No, what is the limit? I'm asking. Safe limit. Yeah, that's the thing.
Yeah.
They said earlier it was 20. Now it is more than 200.
Well, TDS could be different sources, right? So
Yeah.
there are some sources
Yeah.
which
Total
generates
dissolved
TDS,
solid is the
which is not
arsenic
really
phosphatum.
yeah, because the problem is TDS not only arsenic.
Yeah, they are telling them.
TDS could be
Heavy
the
metals.
harmless salt, right? That's the majority, right? If we had a way to measure, I can understand that TDS could be associated with CKDU, saying that arsenic and all the other heavy metals could be there, but TDS cannot be a good indicator because it has many other salts, right?
No, they requested to boil it and drink. Yeah.
That
Is it possible? Is it okay?
I don't know about that technology. How can you remove any of the heavy metals by boiling? You can kill pathogens, right? Uh, yeah, you can make your water microbiologically safer by boiling your water, right? Yeah, yeah, this is this is about microbiology, right? Yeah. Depending on the filter material, you can reduce you can't, probably a certain percentage of heavy metal could be reduced, but I don't know of any filter in the household level which can remove heavy metals, right? Yeah. Carbon will mostly remove organic organic compounds, it can remove, right? Yeah, the heavy metals depending on the state they are, they could be absorbed to the systems. You know, the industrial scale that of course you can have systems with ion exchange like systems, but it's not for the household level filters. You're probably right, because the water board, especially if you are taking from Ambatale, then that water, I believe that water does not have heavy metals, right? It's in a very low level if it is there, but I don't know whether you measure it in the consumers using the pipes, and there could be some, but I don't think that there is a way to come arsenic into that system, right? But boiling water will not help, not even the RO systems, which are so widely used. Because I asked a couple of suppliers of RO systems what technical specification you have. They say, no, we don't need any. This is RO. RO will remove everything. That says everything about that person who is selling, right? And they are saying that, yes, we have highest production, like, you know, the other RO guys, they give only 30% or 50%, we give 70% of water, which means that their process is open. Lot of so it gives a false safety or security to the people. So of course, RO can remove almost everything, but if you choose your membranes correctly, yeah, the policies are there, practices are there, but we have to be aware that it's not, there's no 100% guarantee of any of these things, right? But it's a very good start. If you don't have this, then you don't have anything.
Just leaving. Before I go, I should be thank you very much, because I especially learned a lot of things there. And my storage and water supply to private and private sector, especially digital twin, that kind of approach, scales everything together. Thank you very much for giving that kind of creative ideas.
I think still it is a bit too expensive to have digital twins in most of our facilities, but I think the things are changing. Like maybe in 5 years' time, 10 years' time, this will be a natural part of our utilities. Not only the plant operators, but also the consumers can just go into the web page and see that what is the value there in my drinking water and this stage. So yes, there are many positive things happening with digitalization.
Good evening, everyone. So now it's time for the appreciation. Our resource person actually, definitely we have to appreciate, because I think you are on a short stay in Sri Lanka. You came for mainly for the Candy conference. Not for the okay. So I know that you're for a short stay here. So with very quick invitation and very quick arrangements, we managed to do this one. So I really appreciate, I can see the interactions and that you have this effective coordination. And actually, I'm a highway person, basically. I have done water things, training and all during the university time. After all, I think very few exposure for me. But recently, I happened to join this international seminar conference in water board organized in CESC. It was really, really interesting, and I thought I know something. That was really organized by National Water Supply and Drainage Board. It should be appreciated. That was. So when you talk now here, I thought I can really grab something from you. I can take home. When you started talking about the water supply and management of wastewater, and you're talking about the smart use by design, use, and control. I was trying to grab some more, but it was in a higher level, everything afterwards. You took it very slowly, very effectively, and to a very high level. So wonderful, actually. I must, why not to give a round of applause. So really appreciate. I'm not bluffing, but actually this is what I felt. So I appreciate a lot. And just a small token of appreciation. I think you will accept it.
Not expecting that, but
Really, I don't know what to say. But I know you do this appreciate.
Okay.
Right? I think I'll do the formal vote of thanks now.
Just before you're going, that since you are from the highways, you know, one of the biggest sources of microplastics, that's the highways. Coming from your tires, you're polluting our water, right?
What about damaging our roots? A lot.
So now you know that if you really want to get into the water quality and water safety, that you can do something with that. The thing is that, this is one of the biggest sources of, before we thought that it was a biggest source of heavy metals coming from petrol and all that stuff. But now we are also thinking that we know that it is the source for microparticles. So yes, that's something that we can catch up.
Thank you. Thank you so much for that point. Actually, I'm mainly now expressway consultant, and the highway also maybe touched up again. So, officially, I happen to do deliver the vote of thanks. So first and foremost, the resource person. Thank you so much. I think I told what I had to say. So it's so much effective one and very truthful one. I hope what of support friends and other related people, maybe you have a lot to take home. So thank you so much. And next thing is actually to the participants. If you are not here, I think we don't have any opportunity to get this thing done. So thanks a lot with your busy schedules. And anyway, we are doing this for your benefit. So joining means is your responsibility. And actually, I'm the former chairman of the Civil Engineering Sectional Committee, and nowadays the vice president. Now I'm handling the Continuing Professional Development Committee, and it's another risky thing. You have to coordinate very, very, not like civil sectional committees. This is a standing committee, so I think you better you if you have not joined, so you can coordinate later. With that, I think participants who are online also, thank you so much for joining. There are 3 chats. I don't know what it is. I don't know how to refer. It's okay. So thank you so much for the members who are joining online. And I must thank Professor Ranjit Disanayake, President ISL. Actually, he's the one who introduced our resource person. It's a very eminent person. So thank you, Professor. Though you are not here, my heartfelt thank you note is coming to you. So thank you. And I must thank Engineer Mangal Silva, who did the coordination part. We quickly did it and did it together. So thank you, Engineer Mangala, as the chairman, Civil Engineering Section Committee. And those who supported us in organizing the thing like publicity and IT section and the secretariat. I thank everyone for supporting us. I think I have not missed anyone. And thank you everyone who supported us. And have a safe journey back home, everyone. Thank you. Good night.